So I'm going to try and record this and then as well just post it. So there is also a study guide on Canvas. Just questions, kind of similar to what will be on the final. So section 1 is 6 questions. And then 8 in section 2, so that's chapters 4 through 6. And 11. So it looks like even less stuff on the last. Oh, actually, I think I counted wrong. Let me recheck these numbers. All right, 6 for section 1. And 8 for section 2. Okay, 9 for section 3. Let me see if these numbers add up. Yeah, so that's 29 questions total. Yeah, so there's actually less on the newest stuff. And it's more questions, but they are, like exam 1, there's a 2-dimensional kinematics problem where you have to get multiple equations. So these are much shorter questions. There will be more multiple choice. So yeah, don't let the number scare you too much. Yeah.
Is it multiple choice in the sense of here's a few potential answers and you have to find out what's the right one, or is it multiple choice for example on exam 3 where it's just a scenario and you're supposed to
Oh yeah, not like numbers, pick the right number, none of those.
So it's more like on exams 2 and 3 where it's here's a scenario, what would happen?
Yeah, so the multiple, not solve for the number and then, have a list of numbers. Yeah, so the multiple choice is more the conceptual stuff. But yeah, there's, the problems are just not quite as involved as some of the ones in the regular exams because we have to cover more material in the final. Okay, so you want to go over the kind of newer stuff, like resonance basically. Is that the plan?
And then can we go over some of the stuff on last unit?
Yeah. Sure. So let's talk about resonance. See if I can make up a problem here. Let's say we have a wave on a string. So it's fixed at 2 ends. So let's see what we can ask about this question. I could give you what is a tension, or I could give you the tension and the mass density and ask you to find the velocity, but let's not do that. I'll just give you a number for the velocity. So the speed of a wave on this string is 650 meters per second. So one question would be, what harmonic is this? So it's resonating. So what is a resonance frequency and what harmonic is this? Let's do this. Which harmonic? We'll just call that N because we label frequencies like F1, F2, F3, and so on. So what is this frequency? What is the wavelength? And what is the fundamental frequency? So why don't I give you a couple of minutes to work on this, and then we'll go over it together. You can talk to each other if you want, at least for now, not tomorrow. Wrote down a couple of basic equations.
I didn't even know that was an equation. Like, this is actually, I really don't have time to process this.
Yeah.
Are there units for inches?
Yes.
She got 2.2 on it. But is that the frequency or the angular frequency? So it's not the same as F. What's Fn? What's F1?
So Fn is just the frequency of this.
What's that for?
Fundamental frequency. So the picture would look different for that. So like, yeah, this is just one resonant frequency. So if we looked at F1, that would be a different picture.
I must try FB system with your 2 prime.
So did anyone figure this out? yet.
I don't think anyone knows how to set it up.
Did anyone get step one?
Draw it out, are you supposed to figure out, like, what harmonic it's in?
Well, let's start with the wavelength. Did anyone get that?
That would be one, right?
1 meter, right?
Yeah, because it's.
Yeah, because wavelength is here to, so you have two waves in 2 meters. So the wavelength is 1 meter. Did everyone see that?
Why?
So,
One wave is 2 pumps.
what's that? Yeah, so just like, that's the wavelength. From just, after this it would repeat itself. So a wave is just like one cycle. And it just happens that there's, 2 waves in that 2 meters. Okay, so where can we go from here?
Yeah,
Frequency.
using velocity, since we know that.
Yeah, you know the velocity and the wavelength, so you know the frequency. Everyone agree with that? Let's call this lambda n, actually, because, you can have different frequencies resonating here and different wavelengths. So we'd have 650 meters per second divided by 1 meter. So someone with a calculator, what's 650 divided by 1? Actually, sadly, that's not even a joke anymore. I've seen people do that. But, yeah, so Fn is 650 hertz. Okay. Now, what harmonic is this? Actually, I don't know, but like, how would we figure that out? I haven't done that yet.
You have to do 2 times the length over the number of harmonics equals the wavelength.
Oh, yeah, I guess that would work.
I don't know why.
No, let's draw, the fundamental would look like this. Right? Or maybe a dashed line for one of them. So this is the first harmonic. And then to get the second harmonic, you would put a node in the middle. Now you don't have to draw all the pictures. But the first harmonic, you could say, has a total of 2 notes, 1 at each end. The second harmonic has a total of 3. So what you can do is just count the number of nodes, including the endpoints, and subtract 1. To get to like the next harmonic, you just add 1 node. So in general, the harmonic would be the total number of nodes, which include the endpoints, minus 1. So we have 1, 2, 3, 4, 5. So yeah, you were right. This is the 4th harmonic. Or you could just keep drawing pictures until you get this one. And then you'd see that would be, I don't know if I have room for that. But here we have 2 interior nodes for the 3rd harmonic. And then the 4th. I think it's better just to count the nodes and recognize how that relates to the harmonic. But this is basically that picture. Okay, and then finally, what is the fundamental frequency? Where do we find that? Yeah, this is always true just by definition. So F1 would be F4 divided by 4. So 650 divided by 4. Let's see.
162.5.
Let's say like 163. And yeah, I mean, you can find all the frequencies, like F2 would be 2 times F1, or, you know, F4 over 2. Yeah, and for the wave on a string, you have all of the harmonics. For a half open pipe, remember you only have the odd numbers. So we'll do a wave in a tube problem next. But any questions on this one? Okay, so I'm gonna erase this in the, I'm recording this as well. So I'll try posting this to Canvas this afternoon. But any questions before I erase this? Okay, so let's do a wave in a pipe. And a pipe that's open at both ends is very similar to the wave on a string. So let's do a half open pipe. So, now for, oh, yeah,
You said there's a study guide in Canvas, right?
yeah.
How long is it?
Just a bunch of questions.
Okay, it's just like.
There's 26 questions.
Yeah, so quite a few. Now, the speed of sound, we'll just use the standard 343 meters per second. So, I think, what do I do here? Yeah, if we have, let's say, let's draw the third harmonic and find its frequency. So, draw a third harmonic and find its frequency. I think we have enough information here. Maybe let's do this first. Might as well find the wavelength first and then find the frequency. And while we're at it, let's find the fundamental. Okay. meters. So how does this one go? Anyone, how about the drawing? Anyone do that? Oh, yeah.
Yeah. So we got, do you want me to go up and drive or?
Sure. You'll be on camera, so.
Yeah, sure. So we got 1, 2. I'm not sure why I offered to draw it. I can't. Okay, so third harmonic, so 4 things. 1, 2, 3.
Oh, no, for an open, at the open end, you need an anti-node.
Oh, okay, so it would be open at one side, right?
Yeah,
That's
so
the-
you'll have maximum amplitude at the open end.
Okay.
And, yeah, I guess how many nodes are there gonna be in the third harmonic?
4.
Not 4. Let's actually answer that before drawing. So like the fundamental, well, there's a node at the right end. Because there's always a node at the closed end.
Yeah.
We're looking at like vibration of molecules, they can't vibrate at the closed end. So we have a node there, and let's start with like the fundamental frequency. You have a node at one end and an anti-node at the other, and that's it.
Oh, okay, so it would just be like.
Yeah, that would be the fundamental, would look like that.
So,
And then to get to the next harmonic, what do you do?
but,
Yeah. Yes. You just add one node.
so it would be a
Yeah, they're harder to draw than it
yeah.
looks. Yeah, that's the third harmonic.
Dotted line. Okay.
Okay.
Oh,
So yeah, remember the boundary conditions. You have a node at one end, and an anti-node at the other. Bit of an approximation, but close enough. The anti-node's a little bit beyond the end, but not enough for us to worry about. So that's an important step, is drawing the picture. So I like to start with the fundamental, where you fit the biggest wave that you can, and I'll draw the fundamental as well. So this would be the third harmonic. Now, I guess another question, if you start with the fundamental, which would just look like this, where you just have one node here and an anti-node here, this is the first harmonic. Then, going to the next harmonic, you add one node. Why didn't we call that the second harmonic? Oh, the reason is that it's a half-open pipe which only has the odd harmonics. So if you forget about the harmonics and just look at what waves will resonate, like say this one was 100 hertz, the next resonance will be 3 times that, or like in that case it would be 300 hertz. And so we define that to be the third harmonic. So for a half-open pipe, this is the biggest wave that will resonate in this pipe. This is the next biggest. And if you look at just the wavelengths here, they're off by a factor of 3. Where in like the wave on a string or a pipe that's opened at both ends, it would just be a factor of 2. And so we define things so that this result is always true. So we define harmonics in this way. So if the next frequency that resonates is 3 times the fundamental, we call that the third harmonic. That make sense? Yeah.
So did you imply that when it's open on both ends, they only go in like up even number harmonics?
Not only, they have all the harmonics, like F1, F2, F3, and so on, just like a wave on a string. For a half open pipe, you only get the odd harmonics. So the rest should be easy then, right? Picture's the hard part. So how would we find the wavelength now? I think I heard you talking about it.
We just said divided by 1.5 because we said that we're gonna divide length by 1.5.
So what's this part here?
Well, that's half of a harmonic. Oh, but technically that's one full harmonic, right?
No, what part of a wave is just going from an antinode to a node? Yeah, this is a quarter of a wavelength. And going from a node to a node is half a wavelength. So in total, we have 3/4 of a wavelength would be L. So lambda would be 4L over 3. So like, yeah, this pipe, like this isn't even a full wave. So the wavelength is going to be bigger than the pipe. So we'd have, well, 4 times 2.5 is 10. So this would be about 3.33 meters. Everyone agree with that? Now, how do we find the frequency?
Velocity.
Yeah. I erased the equation, but in general, the speed of a wave is frequency times wavelength. So this would be lambda 3. So F3 would be V over lambda 3. So that's going to be like 100 hertz, roughly, a little bit more. Like 343 divided by 3.33. They don't have a number here.
102.9.
Let's say 103 hertz. And then what about the fundamental frequency?
Divided by 2. The
No.
number of notes. Oh, or the number of harmonics.
Yes. So F1 is F3 over 3. So 103 divided by 3, it's like 34. Close enough. So yeah, the being able to draw these pictures is very important. So you need to know for the pipe, remember you have a node at the closed end and an antinode at the open end. And for the fundamental, just draw the biggest wave that will match those boundary conditions. So like here, just that. This is 1/4 of a wavelength. Yeah, and then, oh, yeah.
Should we focus on the open on one end tubes? Or like,
Well, the one that open on both ends, that's just like a wave on a string, basically.
Okay.
You have every harmonic on that end.
Aren't the number of notes different though?
Yeah. Like everyone is, I think it's better to just draw a picture instead of trying to remember some relation between the harmonic and the number of nodes. Like in this case, we have the number of, for F1, we have 1 node. For F3, we have 2. And then for F5, we'd have 3. So you could find some formula that would match that, but probably wouldn't bother doing that. And I definitely wouldn't try to remember that. So being able to draw the pictures, some people just like using the formulas. Like F1 for, I think it's V over 4L for a half open pipe, or like 2L for an open pipe. If you want to try memorizing the formulas, or I don't even know if they're on the equation sheet or not, but it's very helpful to be able to draw pictures and visualize these harmonics. Everything kind of follows from that. If you can draw the pictures and then just know that from, like one node to the next node is half a wavelength. Like if you look at a full wave, like you start out here going up. After you get to the next one, you haven't completed a cycle because now you're going down. So like one node to the next is half a wavelength, and a node to an antinode is a quarter of a wavelength. So if you can draw the pictures and recognize that, the 1/4 and 1/2, the rest kind of follows fairly easily from that. You can get the wavelength from like the length of the string or the length of the pipe. If you know the wavelength, then you know the frequency. So focus on being able to draw these pictures and get the wavelength. And then everything else should follow. And also maybe just remember for a half open pipe, you only have odd harmonics. I'll leave this up here. Okay, so any questions on this before I erase it? Feeling better about this stuff now? Anyone feeling worse about it?
I'm just worried about the rest.
Like
this
what
stuff's
else?
like everything else we just learned.
So there's mainly this.
I was feeling bad, and then I realized like not much of it is needed, and I'm like, okay, I'm fine.
Yeah, the newest unit actually is the
Yeah, 'cause
smallest
at the start you
number,
were
I
gonna say
think.
like a significant portion, but it was like not that much at all.
Yeah. No, especially during the summer, you don't really have time to get all this stuff. So,
So focus on harmonics, not like resonance and.
this is resonance, yeah.
Okay.
Now, one other thing, interference. Remember like delta, that stuff?
Let's review it.
Okay. That would be,
And the sound waves and stuff, like I can do the very, very basic problems. It's just when it's not super basic, I literally have no clue where to start.
so it sounds,
Like, like the beta equation.
oh, intensity,
Yeah.
decibels, yes.
Yeah.
Okay. Let's do an interference problem, like constructive or destructive interference. We'll talk about intensity, and then there is something about section 3 on rotations. We should have time to get that in as well. So yeah, I'm going to try and make up a problem. This might be, because normally, if I just make up numbers, we're probably not going to be like in a condition where we're constructive or destructive. That would only occur at like certain distances. So making up a problem might be difficult. Let's focus on the idea. So let's say we have two sources of sound. And we have an observer somewhere. Now, we can make a right triangle to make the geometry easy, but there's a problem like that in the notes. Maybe let's do this. Let's just have a one-dimensional problem. So let's say we have an observer over here. Now, I'm going to change this picture a little bit. We'll just put S1 and S2 closer together. Let's say this is nine centimeters. So these two sources of sound are producing identical tones. Let's say the frequency is 220 hertz. We use our standard speed of sound as well. And let's find out how far from, say, S2, that would be easiest. How far from S2 should we place the observer to here? Let's find both constructive and destructive interference. So like, now there's multiple places where we would find constructive interference and destructive interference, but let's just find like the first two. So remember the condition, I'm just going to write a shorter version of this. So delta is the path length difference. And so, path length difference of half a wavelength will give us destructive interference. Now, delta equals 0 would give us constructive interference, but that would only occur if this point was like in between the two speakers. So let's rule that out. So we have to place, so we go to the next one, let's say delta equals lambda. And I think this should work out. So what we want to find is X for constructive interference and X for destructive interference. And I'll give you a couple minutes to look at this before we go over it. Yeah.
Is that, like, the symbol equals lambda, is that a delta or is that an F?
This symbol?
Yeah,
That's delta.
thank you.
Yeah, it's a Greek letter.
What do you think would be more useful, the homework or going over like these individual worksheets? Like, are these too difficult for what's going to be on it?
The individual, those,
Like if we had to choose one because it's more abstract.
yeah, there's limited time. Yeah, maybe for kinematics, those worksheets are maybe a little,
Oh, I'm
more
talking
too
just about the new
complicated.
stuff.
yeah, the worksheet, like, there's a harmonics worksheet, that's worth going over.
Okay, I did that.
Yeah, like, the kinematics on the exam will not be the same level as the worksheet, so it'll be more straightforward.
Okay, cool.
Yeah, significantly easier than, like, those worksheets.
So would it be best to just go over the exams, like the past ones?
Yeah, except those,
I've already done that. I'm talking
yeah, I
about
mean,
the
just
new
think the
stuff.
final hopefully will be easier than some of those problems.
Okay.
Because, yeah, I wanna cover a lot of material, so more questions, but the same amount of time. So, yeah, nothing where you have to put too much together.
Like, where do you recommend we look for, like, the new stuff, like stuff that would be exam 4?
I think that harmonics worksheet is
Just that, okay,
good, and, yeah, it doesn't cover like this.
yeah.
So, yeah, just, yeah, like over the sample problems, or I'll post the solutions to the homework today at 6.
Okay.
And, yeah, I guess just problems that we've done. Look over that for interference. Okay, so what's the first step here? Okay, these, I'll just say F. Because they're both producing the same sound at the same frequency, and they are in phase with each other. So what would the first step be?
Solve for lambda.
Yeah, let's find the wavelength. So the wavelength would be the speed of sound over the frequency. A hertz is, you know, like cycles per second. So we'll get the wavelength in meters here. So what's 343? That's like 1.5, right? Somewhere. 1.65? Like, so lambda is 1.65 meters. Okay. Now, what is delta in this case? What's that?
0.825.
Yeah, I'm starting to question if this problem even makes sense right now. Yeah, so it's a one-dimensional problem. So, yeah, like delta's a path length difference. So like from S1 to the source, like that, let's call that D1. So this is D2 here. So delta is just 9 centimeters. Yeah, I'm starting to think this problem isn't going to make sense. Yeah, delta is going to be the same regardless of where the observer is. So yeah, I've never done a one-dimensional problem before. So yeah, delta is going to be the same regardless of where that observer is. So yeah, I wanted to avoid doing like a right triangle because that was in the notes. So it's like just redoing something that's already there. So yeah, sorry, but this problem kind of doesn't make sense. Because it doesn't matter if we move the observer around, delta is always going to be 9 centimeters. So solving for x, yeah, that's not going. So I wonder if we can save this and, yeah, the only other geometry I can see that would make sense, or that would be fairly simple, would be making this a right triangle. Because we want delta to depend on where the observer is. So, Yeah, sorry, let's revise the problem. Let's call that x. So again, now this is similar to what we've done before, but why don't we, it'll be a review. So this distance here is 9 centimeters. Yeah, sorry, I made a problem that made no sense at all. But now if we vary x, the path length difference will be different. So, yeah, let's try this then. So the path, that's kind of the next step. We want to relate delta to x. So like this is d1. D2 is just x. Let's call this, let's give this a name. This length here. Not sure what to call it. Let's just call it C. So D1 would be C squared plus X squared. So we can solve for D1 as like a function of X by taking the square root. And D2 is just X. So the path length difference would be D1 minus D2. So we're going to end up with a quadratic equation, looks like. But any questions on just using geometry to find delta?
Well, then what do you plug in for like C and X?
Well, C is 9 centimeters, X is what we're trying to find. So if we look at constructive interference, let's look at delta for constructive interference. That would be half of a wavelength. So that'd be what, 0.83 centimeters. Or 0.83 meters, like 83 centimeters. So just the wavelength divided by 2. So I think that's 0.825, let's just round off. And for constructive interference, delta is 1.65 meters. So then what we would do, like for XC, we would have this equation. 0.83 meters would equal, we'd have C, which is 0.09 meters squared, plus we're doing destructive interference. So we would basically just solve that equation. Yeah.
And then, sorry, I know you've gone over this, but when is it destructive versus constructive?
So destructive is when the path length difference is half a wavelength. And constructive is either 0 or a wavelength. And in general, there's more deltas that will give you constructive or destructive interference. You can always add a full wavelength to either of these. Because adding a full wave, you're back to the same phase.
Like for this problem, how would we know whether it's destructive or constructive?
Well, we want to find both. Like, what would X have to be to get constructive interference? Or what would X have to be to get destructive interference? And so basically we find delta, we know what C is, and we know what delta, but we have to solve for X. And because we have limited time, let's not actually solve these, because it's quadratic, and it'll be kind of annoying. Like we'd square both sides to get rid of the square root. So, yeah, it would end up, actually maybe it would, yeah, this would be a rather annoying algebra problem to solve. So you won't have to do this on a test because just the algebra would be time consuming. But this is a solvable algebra problem. We have an x squared under the square root and an individual x. So we'd have to square both sides of the equation, which would mean foiling this. So it would be, you know, something you could do, but not something that we want to do. So that's the problem with just making up problems.
But on the test, we'll have numbers that are solvable.
Yes. I mean, well, this is solvable, but you'll have numbers that are reasonable. Let's put it that way. But yeah, the basic idea is you use geometry to find how like x and delta are related. So, you know, first find the wavelength. Recognize the conditions for constructive and destructive interference, and then it's geometry, which will be more reasonable on the exam. Yeah.
So like the difference between constructive and deconstructive, like deconstructive is the one that like cancels out? Or-
Yeah, so if these are speakers, and you were at the right location, you know, like you could have one speaker and you would hear sound from it, and then you turn on a second speaker and you wouldn't hear anything. Kind of a weird, seems weird, but yeah. And supposedly they have these noise canceling headphones where it kind of detects the sound wave coming in and creates another sound wave to kill that off. I'm a little skeptical if they actually work though. They do? You have one or you?
Yeah.
Oh, okay. Yeah, it's a very complicated thing. Well, I have heard other things like a soundproof room that kills off outside sounds. I wouldn't believe that one because it would depend on where you are in the room. But yeah, I guess noise canceling headphones could be a thing. Okay, so yeah, the exam question. Let me just check. Is there one of these? I think there is. It'll be much more reasonable than the one I just made up. It's actually a true story at Harvard. This guy was teaching his grad students, and during in the middle of an exam, the teacher's like, "If anyone figures out number 6, let me know. I couldn't get that one either." I mean, it's for grad students, so that's fine.
Candy?
What's that?
No.
Oh, okay. So yeah, the one on the exam will be a much more solvable problem. So we reduced it to just a known algebra problem, but any questions on the basic idea? Yeah.
What is D2? Where does that come from?
Oh, so D1 and D2, D is the distance from the speaker to the observer. So like D1, D2 is just X.
Okay.
So yeah, distance from the speaker, from like each speaker to the observer. And the reason there's a phase difference between the two sound waves is because of the path length difference. Okay, so now we have decibels. Seems like we're really focusing on the most recent material. But any questions on this before I erase it? All right, so a couple of things on decibels. Covers everyone's favorite topic, which is logarithms. So and again, this is on the equation sheet, so you don't need to memorize that formula. So intensity, that's measured in watts per meter squared. Those are the basic SI units. And beta is the decibel level, measured in decibels. And I naught is the lowest sound that a typical person can hear, which is 1/1,000,000th of a watt per square meter. So it's an amazingly small number. Your ears are pretty amazing at detecting sounds. So, yeah, there's two things that we would want to focus on here. One is, if we're given an intensity, what is the decibel level? And that's, in theory, a simple matter of just plugging it into the formula. If I give you I, just plug it in. Again, let's do one of each. So we'll do that. If I give you the intensity, find beta. Or if I give you the intensity level, like in decibels, what is the intensity in watts per meter squared? So the first one is more direct. Let's say we have an intensity of 4.2 times 10 to the minus 7 watts per meter squared. So what is the intensity level? And again, I highly recommend doing this algebraically. Ideally, the only thing you do the calculator for is taking the logarithm of a number between 1 and 10. And you can just plug it in right away if you want, but let's do this a little bit let's do as much algebra as we can, because calculator mistakes are one of the most common mistakes that people make. So let's just plug in. I'm not going to put the units because they're going to cancel out. So if we just plug in I, we've got that. So let's work out this in the parentheses first. So 4.2 times 10 to what power?
Is it -5 or -19?
Close on one of those.
Is it the fifth?
5, yeah, positive 5. So let's do this. Well, there's two ways you can do it. One is if you have the same base, you take like the top number and subtract the bottom. So you have -7 minus -12, which is -7 plus 12. So that would be 10 to the 5th. Another way would be to multiply the top and bottom by 10 to the 12. Because 10 to the minus 12 times 10 to the 12 is 1. So you just get rid of the denominator there. So either way you like. And again, I would do one more step algebraically. Because this logarithm, you could write logarithm of 4.2 plus 5. Because log, it's, plus log of 10 to the 5th, but log of 10 to the 5th is 5. So what is the logarithm of 4.2? Like 0.6 or something? Don't have log of 4.2? Natural, or not, base 10 logarithm of 4.2? 0.62. So multiplying that by 10, that would be 6.2. So we'll have about 56.2 decibels. So, any questions on that? Okay, So I'm going to erase this, and now we'll do like the inverse problem, where I'll give you an intensity in decibels, and we want to find watts per meter squared. So any questions before I erase this? Okay. So, actually I'll leave this. Just erase this part. So let's say we're given a decibel level of, let's say 92. So what is the intensity of that wave? So we're using the same formula and just plugging in 92, but now we're trying, like, when we're given I, we have a formula directly, just plug it in and do the calculation. But here, what we're trying to solve for is in that logarithm. So let's start out by, I'm going to rewrite this algebraically. Let's say logarithm of I over I naught, that would be beta over 10 decibels. So basically just take that equation, divide by 10 decibels, and if we plug in 92 on top, we just have the number 9.2. The units cancel out. So how would we get, so we have the logarithm of I over I naught is 9.2. So how do we get I naught itself, or I itself? What's that?
Would you do 10 to the 9.2
Yes.
equals I over the I naught?
Yep.
20.
So yeah, remember when you have like logarithm of something equals 9.2, that 9.2 is the exponent. And we're dealing with base 10 logarithm, so we have 10 to the 9.2. Now I think this is on the formula sheet as well, if you don't. I know you've seen, it's one of those things where you've seen it, but if you don't use it much, you never really learn it. You've all seen it before. And then we can, you can just do 10 to the 9.2. Well, let's do one more step. We have 10 to the minus 12 watts per meter squared. So this would be like 10 to the minus, what is that, 2.8, or is it 1.8? Yeah, 1.8. Or you could do like 1 over 10 to the 1.8. Wait, isn't it,
2.8.
yeah. So yeah, you could, in your calculator, do 10 to the minus 2.8 or 1 over 10 to the 2.8.
Wait, could you just, in your calculator, could you do 10 to the 9.2 and then press enter?
Yes.
And then multiply it by 1 times 10 to the negative 12?
Yes.
Okay.
Can we get an answer for this?
I got 0.0016.
So it's 0.0, let's say 1.6 times 10 to the minus 3 watts per meter squared. This is a reasonable number. So like the hearing range is from 10 to the minus 12 watts per meter squared to like 10 watts per meter squared, which you never want to experience that. That would quickly destroy your hearing. So this is a reasonable number 92 decibels, that's fairly large. That might even be damaging over a long, if you hear sound at that level for a long time, that could damage your hearing. It's kind of interesting that, like your ears, like, like your eyes go bad as you get older. Your ears aren't supposed to do that, but they do. But that's not normal. It's because of just the society we live in. We're exposed to much more noise than, we would be like 1,000 years ago. So, yeah, we're not by nature exposed to loud sounds very often. So we consider it normal to lose your hearing as you get older, but that's not really supposed to happen. Okay, so any questions on decibels? All that fun stuff. Did you have something in mind for like rolling motion or circuit like that? Sure. We have time for one quick problem maybe.
Could you problem like torque, yes?
So something with torque?
Yeah, like one of those long problems from the last year.
Oh, like statics?
Is that what that is?
Yeah.
Where you, okay.
Where you need to find like the center of like rotation or whatever. You have like a length and it rotates.
So, center, find the axis of rotation. Oh, like, so, yeah, you have to pick that one, you mean?
Yeah.
Okay.
Is that gonna be on it?
There will be a torque, like, statics problem on it.
Like a hanging sign one?
More like the wrecking ball one. It will be not so bad. Let's do something similar to the last exam where we have a pivot here and say we have one mass here and one mass over here. Or maybe let's say this is like a movable support. So like we can slide this over. So let's say the length of the whole thing is 4 meters. And say mass 1 is 2 kilograms and mass 2 is 3 kilograms. So like where do we want to put this support? Like say this is a thing where you could, this can slide across this bar. So like, let's call X the distance from mass 1. Where do we want to put X to balance this object? Let's ignore gravity. Let's say it's a light object. The bar itself has an insignificant mass. So let's ignore gravity. And so we're just looking at basically, there's 3 forces acting on it. There's the weight from each mass, and also there's an upward force at that support. So where would we want to pick our axis of rotation? Yeah.
At the support.
Yeah, because that gets rid of this, this upward force. So we have 2 torques here. We have M1G and M2G. And the distance from mass 1 is X. What is the distance from the support to mass 2?
4 minus X.
Yeah. So like X plus L minus X is L. So if you just add those 2 pieces, you get the total length. And so in equilibrium, the net torque is 0. So there's 2 ways we can do this. We could say net torque is 0, one of them is positive, one is negative. Or we could say torque clockwise equals torque counterclockwise. Does anyone have a preference?
Equals 0.
Equals 0. Okay. So let's look at this one. Is this a positive torque or a negative torque? So what type, the M1G, is that a clockwise rotation or counterclockwise? Counter. Yeah, this is a pivot, it's going to try to spin it this way. So this will be a positive torque, which would just be the force times the distance because they're perpendicular. The bar is horizontal, the forces are vertical. If there's an angle, you'd have to find the lever arm, but in this case, the lever arms are just these distances. And then for the second one, we have minus M2G times that distance, which is L minus X. So basically what we want to do is solve for X.
What is it minus M2G?
Oh yeah, so this one would be a clockwise rotation. So by our convention, counterclockwise is positive, clockwise is negative.
How do you know that though? Without the arrow being curved? Because I can do it with the right hand rule, but if the arrow's going straight down, I get so confused.
Oh, so just look at this force by itself. Like if you pull on the bar, it's going to go this way. If it's rotated about that end, it's going to go clockwise.
But then couldn't you do the same thing with that one?
You could.
Well, yeah, this one's going to go this way because this end of the bar, like picture that point is fixed, so it's got to go that way.
And the point of rotation is arbitrary, so you can choose which direction it is. There's just
Yeah.
one negative, one positive.
Yes, it's a convention, just like right is positive, left is negative, but you can change that if you like. So, yeah, that would effectively just multiply this equation. That's negative, that's positive, it's the same equation. It's multiplied by -1. And so let's distribute this. Okay, let's cancel out G. That doesn't matter. So we have M1 times X minus M2L plus M2X equals 0. So just got rid of G because we have 0 on one side. So again, if you go to Mars and do this, you get the same result. And let's isolate the terms involving X. So we have M1X plus M2X. And let's move this other term to the other side. And so X, I'm going to write it this way. Just to get, unit-wise, M2 divided by M1 plus M2 is just going to be a number. So we'd have 3 divided by 5 times 4 meters. So that would be 2.4 meters. And again, that makes sense because 2.4 meters is more than halfway. And that makes sense because M1 is smaller. So, like if this is the midpoint, we'd have to have the support over here because M1 and M2 are fighting each other. And the torque depends on the distance, so the smaller mass would have to be a greater distance so that they can balance each other. Okay.